Today, on how it's made. Manhole covers. Fitting a round peg into a round hole. Range hoods. A stovetop's biggest fan. Artificial logs. The secret behind those fiery fakes. And snowmobiles. A far cry from a one-horse open sleigh. Manhole covers are those metal lids on maintenance holes in roadways. Workers lift them to enter and repair sewers and other underground utilities. Foundries make the covers out of heavy-duty cast iron, so they last for decades and don't budge under passing traffic. This company makes hundreds of models of manhole covers and collars, the rims upon which the covers sit. They come in two types of cast iron alloy, either ductile iron, which has magnesium to reinforce it, or gray iron, which is heavier but just as strong. To make a cover, they first have to make a mold. This one's got the design of the cover's top side carved into it. Workers pour in about 300 kilograms of sand mixed with glue and a hardener. For the underside of the cover, they repeat the step in another mold. A worker creates a channel in the sand mold through which they'll pour the molten metal. He plugs the hole with a wooden block to preserve the cavity beneath. He removes the block and briefly reinserts the pipe to ensure the cavity hasn't caved in. It takes about 15 minutes for the sand mix to harden. A machine then inverts each box and vibrates to shake out the mold. To make one manhole cover, workers will join molds of the top and bottom sections. Alignment lugs and glue between the sections help them align properly and form an airtight seal so molten metal won't leak out. Next, a machine flips the bottom mold, moves the top mold into position below, then mates the pair. The factory buys scrap metal from demolition sites and also recycles its own. It'll melt these metals with certain minerals to enhance the mix. Graphite to make it malleable, silicon to make it stronger, and magnesium to make this batch of ductile iron lightweight yet strong. Here, a giant magnet picks up chunks of recycled iron and steel. The metal is preheated to 420 degrees Celsius, then transferred to a furnace. There, at 1500 degrees Celsius, it takes about a half hour to melt enough metal to make 35 covers. Workers then transfer the molten metal to a cauldron and add more silicon. This evens out the consistency so it's easier to pour. Besides the channel for pouring in the metal, some larger molds have vent holes to evacuate burning gases. It takes about an hour and a half for the metal to harden. A conveyor then drops the molds into a container and breaks them open. Using a hook, they pick up the casting. This one's a collar weighing about 100 kilos. They knock off the remaining bits of sand and excess bits of metal that formed during the casting. These scraps get recycled into a new batch of iron. Manhole covers vary in size according to the specifications ordered. Most are roughly the diameter of a car tire. The average weight, about 63 kilos. A worker now smooths out the edges of the collar and then the perimeter of the cover. This way, it'll sit flush on the collar. This machine tests the strength of the cover by applying pressure. It must withstand the weight of a car on every 2.5 centimeter area. They paint the covers and collars by dipping them in a bath of black tar. Once dry, the pieces have a rust-resistant finish that lasts for decades. And the buyers expect them to last because a manhole cover and collar cost up to $1,400. People have cooked on stovetops for centuries, but it wasn't until about 1800 that metal stoves with flues vented steam and smoke outdoors. Today, factories make encased fans that powerfully ventilate and also light the stovetop. A stovetop is often called a range, hence the name range hoods. No matter how well you cook, steam and smoke are inevitable. Fortunately, the range hood's fan, called the blower, clears the air in seconds. Production begins with this computer-guided machine. It cuts out a sheet of galvanized steel to make part of the hood's housing. A 300-ton press then perforates the sheet and cuts out up to 50 openings for screws, wiring, and exhaust outlets. A worker inserts another panel for the housing in a 25-ton press. The machine bends the steel in 2 places. They'll use this component to make a circular channel that evacuates smoke and steam that often contain grease particles. To curl the panel, the worker uses another machine with 3 rollers. It forms the circular channel that fits around the blower to direct air out through the exhaust. Here, a spot welding machine joins 2 corners of the hood's housing. This is mainly for aesthetics. A weld looks better than a screw or bolt. This 80-ton press bends the hood's shell, making one of 8 folds that give the component its final shape. Now, a worker removes a plastic coating that protected the steel during the cutting. He applies a sticker with a product ID code. Then, a pad printing machine marks the brand name, one of 12 this factory produces. This is the first of 8 stops on an assembly line. A worker installs a transformer to power the blower's motor and 2 halogen lights. This circuit board regulates several functions, including 3 light intensities and the blower's 4-speed motor. She attaches the board to the housing with 3 screws. This panel has lights that indicate what functions are on. Next, the worker installs the blower's 165-watt electric motor. The motor attaches with 3 screws into rubber bushings that reduce noise. Then, light sockets made of heat-resistant plastic. The blower's housing snaps into place around the motor. A little silicone on the housing ensures an airtight seal around the blower. Then she installs the blower wheel. Next, she plugs in the lights to test them. You press this button 3 times to make the light increasingly bright. There's 1 button for each of the motor's speeds. After snapping a panel on to enclose the hood assembly, a worker attaches a plastic ring to direct air through the blower. A computer system tracks each model's assembly. When workers complete a step, they input it into the system. An optical scanner also senses when they remove a part from one of 25 cubbies, like these removable air filters made of mesh aluminum. The tracking system's called Poka-yoke, a Japanese-inspired method that ensures thorough assembly. It follows each model until workers place it in a box for shipping. The system's final task is to ensure they put in the mail-in guarantee card and the installation manual. If workers forget anything, the system reminds them with a loud buzzer. Once they staple the box closed, a machine with suction cups picks it up and stacks it, 10 boxes per pallet. All this work so you can stay in the kitchen even if you can't stand the heat. In the mood to light a cozy fire in your wood stove or fireplace? No need to put on your coat and boots and trudge through the snow to the outdoor woodpile. Nowadays, you can buy a box of man-made logs. A lot less hassle for you, fewer trees die, and the environmentally friendly brands pollute less and are safer for your chimney. These artificial logs are made entirely of compressed sawdust. Their moisture content is less than 9%, compared to 30% in real firewood. The compression and dryness combined make these man-made logs easier to light than real ones. They don't throw sparks while burning, and they produce 300% more heat than real firewood. The high temperature burns up the gases better, so the logs emit up to 50% fewer pollutants, and they produce fewer ashes and far less creosote, a highly flammable tar that's a natural byproduct of wood burning. Creosote buildup in a flue can cause a chimney fire. The sawdust comes from pure natural hardwood, mostly oak and maple. The log company buys it from factories that make hardwood flooring. So, from the start, these logs are ecological because they're made of recycled waste. The sawdust is clean, and the log factory doesn't add chemicals, so it's safe to cook over the fire. The sawdust moisture content is so low because the wood it came from was already dried in huge ovens to make the flooring. The sawdust arrives in different consistencies, so the first step is to put it through a grinder to make the particles uniform in size. The next step is the key one, compression. At a rate of 2,500 kilograms per hour, an air-blowing system moves the sawdust from the grinder directly into a compression machine. The machine is a giant cylinder with a piston that moves inside. The piston compresses the sawdust using extreme high pressure, 1,400 kilograms per square centimeter. The result is a 12-meter-long compressed sawdust log. Unlike some other brands of artificial logs, this one contains no binding agents, which can pollute the air. So how does the sawdust stick together then? The secret is the high compression. The intense heat it creates bonds the natural resins in the sawdust. As the log exits the compression machine, a cutter shapes the flat edge. This is a safety feature. With the flat edge on the bottom, the logs are easier to stack in the recommended 3-log configuration, and they don't roll out of position. Now a guillotine chops the 12-meter log into 40 smaller logs, each one 30 centimeters long. A separator pulls them apart. The company also produces a 27-centimeter log. The logs drop onto a conveyor belt that leads to the packaging area. factory boxes its logs with instructions and 2 fire starters. The starters are made of sawdust and candle wax, more effective than using newspaper to get the fire going. This competitor's artificial log breaks easily because it isn't as dense. This company's log, on the other hand, is more solid because it's so tightly compressed. That high density translates into more burning time. 3 logs will keep your fireplace alight for about 3 hours. For centuries, inventors tackled the challenge of snow travel with determination and frustration. The first snow machines trudged through winters awkwardly and slowly, but by the late 1950s, new technologies and materials emerged to make snowmobiles that could blaze through the snow with increasing ease and comfort. Snowmobilers often face rugged terrain. Snowmobiles need a rock-solid build to keep the riders safe and comfortable. It all begins with an aluminum alloy frame. The pieces arrive partly assembled to the radiator. A robot spins and positions the frame. A computer-guided frame rivet machine punches holes and inserts rivets directly into the frame with great precision. This process bonds the parts tightly so they can't vibrate. Next comes the rear suspension, aimed at making the ride as smooth as possible. Inserting this plastic slide onto the runner minimizes friction between the track and the suspension. A conveyor belt carries the suspension system through several stations. Wheels and sprockets will turn the track that grips the snow. The suspension kit, with springs and coils, goes directly into the runners. Along with these shock absorbers, the suspension will fit snugly into the snowmobile's frame. Workers tighten everything manually for now. Later, a machine will tighten things even more. Assembling the transmission system starts with this countershaft. First, they install a high-performance brake disc made of forged steel. The chain case fits snugly on top, thanks to the ridges on this ring. This die-cast aluminum casing will house 2 gears and a chain. This bolt connects to a spring that keeps the gears and chain tight as they turn. The chain tightener must slide smoothly back and forth in its groove to keep the chain's tension even. This test checks that the spring expands and compresses properly. Now comes the oil gauge. It's essential that oil lubricate the parts thoroughly because the motor will generate a lot of friction. The transmission fits on top of the frame. These coils, springs, runners, and wheels fit easily into the rubber track. The rear suspension system connects to the track system, while this white plastic sprocket connects the track to the transmission. The speed sensor attaches directly to the sprocket. Four high-grade steel bolts anchor the rear suspension system to the frame. They're so strong that the suspension can withstand the vibrations that come with high speeds. Now for the engine assembly. Bolts attach the electric starter directly to the engine. The fuel-injected engine generates a lot of heat, up to 700 degrees Celsius. This shield has layers of insulating wool that act as a heat barrier to protect the driver from scorching hot exhaust. The engine's made of cast aluminum, so it's relatively light, just 45 kilograms, and it propels the snowmobile up to 200 kilometers an hour. Now for the front of the snowmobile. This front suspension system requires a different assembly from the rear one. A hoist brings it all together. The gas tank is made of lightweight molded plastic rather than metal. The throttle controls the speed, just like a gas pedal in a car. They install the throttle assembly, and a few more functional details. These lightweight aerodynamic plastic side panels give this snowmobile a sleek look. And now, the final step. The zero-gravity hoist lifts it all onto a skid. Polystyrene sheets protect the snowmobile during transport to the retailer. From start to finish, it's taken 3 hours to assemble this showroom-ready snow traveling machine.